So let me begin the recording part. Okay. Any questions about the worksheet I sent out on Tuesday? Any questions? So I assume that you all understand at least most of it. So for today, we'll be discussing, first of all, I'll be discussing about the strategies for determining if a given series is converging or diverging. Since now we have learned so many things, different tools to do that. And secondly, I'll be doing something about the finding the radius and the interval convergence for given series as the second part, which will be everything we'll be discussing today. Okay, so let me begin with the first part. The first part is about the strategies for testing series. Okay, so this is the first topic we want to do. Let me actually say, okay, this is much better. So the first strategy that I want you guys to always keep in mind is we first need to understand the special cases. What are the special cases? Number one, if the series is of the form summation 1 over n to the p's power. So this is the p series. And we know it's converging when p is larger than 1 and diverges when p is smaller or equals to 1. So this is the very first, very special case you want to remember. This is the most important case, the p series. And secondly, if the series is of the form summation a to the r to the nth power, which is a geometric series. So this is a geometric series. Then we know that this one converges when r absolute value is smaller than 1 and diverges when absolute value of r is larger or equals to 1. Be careful here, it's the absolute value of the ratio, which is what matters, okay? And more importantly, when this is true, then the summation actually equals to a over 1 minus r, where a stands for the initial term. So sorry for the confusion about the notation, but if I'm writing over there, then the n goes from 0 to infinity in this case. So that the initial term for the series now is given by a exactly, okay? So be careful with this subtlety here. How do you compute that? This is the initial term for your geometric series, the very first one, okay? So once we understand these two basic cases, the base models, then the remaining thing is how do we use these together with the comparison principle to find out the other series. So the third one is if a series has a form, maybe is similar to either one of the above, either one of the above, meaning it's similar to either p series or geometric series, then we use comparison principle or limiting comparison principle. Remember that I mentioned about these last time when discussing the comparison principle. So the limiting comparison principle is actually more useful in terms of doing this kind of computations or testings. So I'm giving some examples later on for number 3. Is whenever you have a series which you find out has a form which is very close to be a geometric series or to be a p series, then you do the comparison principle. Okay. Any questions? Any questions so far at this point? Okay. So for number 4 is actually one of the most important techniques that I want you to do every time at the very beginning. if a series satisfies limit an when n goes to infinity is not 0, what can we see? Suppose you have a series such that the nth term doesn't go to 0 as a limit. Can this one be converging then? Then by the nth term test, this is so-called nth term test. What's the name for this testing that Dr. Chadwick used in class? Does he mention this actually as an nth term test or as a divergence test? Anyone know this? Okay, so I'll call it divergence test, I guess. That's actually more intuitive, divergence test. Then by the divergence test, then this will imply that this means an diverges. Okay, so actually as a schematic way to solve a testing problem, I want you guys to do number 4 always at the beginning of your problem. So always try to see if the nth term goes to 0 or not at the very beginning step. So this is actually what you should be doing for the first try, actually, to find out if the nth term goes to 0 or not. Then you do everything else. Okay, then you find out comparison principle, p-test, geometric series, things like these. Okay, but before you do anything, of course, I mean, if you find that it's already in the form of a geometric series or in the p-series, then you have the criterion then. But I'm talking about an arbitrary Jenner like series. This should be the first thing you do, actually, using the divergence test. Okay. So with number 4 here, this is the 4th term. Okay. So number 5, if the series is of the form -1 to the nth power bn, or -1 to the n minus 1th power times bn, the summation of that, meaning it's either starting from the negative term or starting from the positive term, depends on which one it is. Then you use we use the alternating series test. Remember that I mentioned last time, alternating series test. So basically, you have to test 2 things. One is decreasing. Secondly, it has to be going to 0. The limit of an has to be 0. Okay, so decreasing to 0. An has to decrease to 0. This is what it means. Okay, if this condition is satisfied, then the series is actually converging. Not only that, remember we have a good estimate of the error term for the partial sum approximation there. Okay. So number 6, this is for alternating series test. Number 6, if you see n factorial, or maybe n to the nth power, things like this involved, usually this is an indication of using a ratio test. Okay, this is a very clear, like a clear clue that it's a hint that you're going to use ratio test in these 2 scenarios. Okay. And the number 7 is the following. If an equals to fn, where f1 to infinity fn dn, fx dx can be evaluated easily, then use integral test. Okay, this is the very last one that will be used actually for the final exam actually. So all this actually be exhausting the possible scenarios you'll be encountered on the final exam. Suppose you're given a testing problem. it won't be a straightforward, for sure, it won't be a straightforward 1-2 kind of question. It won't be a geometric series, and it won't be a geometric series. It's not going to be something as easy as these. Suppose you are given a geometric series, usually you will be asked to find out the numerical value of the geometric series using some formula like these, okay? By doing some algebraic manipulations to put it into the standard form, and then using this formula here. But generally, it should involving comparison principle or using ratio test in some sense to do the testing, okay? And last year, actually it's not last year, in 2018, the final exam actually is about integral test. Okay, so that means every possible test you have been learning so far is actually possible for the final exam, actually. So let's do some examples to see what this means. Example 1, summation n goes from 1 to infinity, n minus 1 over 2n plus 1, okay? You see that, so first of all, let's see. If any kind of series, give you any kind of series, first thing is you want to isolate, or in some sense, you want to find out what's the closest form this one is, whether this is close to be a geometric series or this is close to be a p-series. In our case, obviously, this one is close to be a p-series. This is close to be a p-series. It's a perturbation of a p-series. That should be the more accurate language to see. So this is more close to be a p-series. But remember that before we do any kind of comparison, always remember to do the number 4 here to see if the divergence test can be used to this case. But you can see that in this case, when n goes to infinity, n minus 1 over 2n plus 1 actually equals to 1/2, which is now 0. So by divergence test, you are done, right? This is going to be diverging for sure. Okay, so this is diverging. By divergence test, the series diverges. Okay, you see how easy that is if you can find out the nth term limit. Okay, if it's non-zero, you are done. Okay. What about the let's see another example here. Now we have something more complicated. Let's see, this is from n to 1 to infinity, square root n cubed plus 1 over 3n cubed plus 4n squared plus 2, okay? So again, we are trying to determine if this one testing, if we want to test if the series is converging or diverging. But in this case, again, we do the following is, to which series is this one close to be, right? Let's see, determine it from the numerator and denominator. When n becomes very large, the numerator is almost like a square root of n cubed, right? When n is large. And when n is very large, the denominator is almost like a 3n cubed, right? But I mean, the 3 is fixed. So roughly speaking, we have something that's close to be this, which is actually n to the 3 halves 1, right? So roughly, this is the one we get. And what kind of series is that? I mean, you can see very easily this is going to be a p-series, right? This is actually a p-series. So the p in this case actually equals to 3 halves. Okay, any questions so far? This should be easy to see, right? I mean, this series, given the form, is definitely going to be a p-series, close to be a p-series. And you can almost determine the major terms in the p-series given by 1 over n to the 3 halves. The question is, whether this one is converging or diverging. Let's first do the divergence test. But as we just argued, because the numerator behaves like n cubed taking square roots, whereas the denominator is like n cubed, So the limit will definitely go to 0, right? It's almost like this, right? So the limit is actually 0. So the divergence test doesn't tell you anything. Actually, the an goes to 0 as n goes to infinity. Okay. Suppose we know that, then the next step is to see, and also we know that we are definitely going to use comparison principle, but how do we use that, right? That's the problem. But let me remind you guys, in this case, I want to use the limiting comparison principle. So in this case, we are going to find the limit as n goes to infinity of root n cubed plus 1 over 3n cubed plus 4n squared plus 2 over 1 over n cubed over 2, so 3/2. So this is our original question, and this is our model case, right? The closest p-series we know to the given form, and the limit of that actually equals to 1 over 3rd, 1/3, which is non-zero and finite. Hence, they satisfy the same diverging of converging properties. But we know in this case that this is as the p-series is converging because p equals to 3/2. So that means the original question also converges because of the limiting comparison principle. So what does this equality means is that when n becomes very large, the nth term of the original series is almost like 1/3 of this p-series, which we know is converging, right? So roughly speaking, this original series is like 1/3 of a given p-series where we know it's converging. So that's why this one should also be converging here. Okay, so you see the power of using limiting comparison principle without doing any kind of inequalities in this case. Okay. So this is the first example, the third example. And then the next one is, what about this series? N times e to the negative n squared from 1 to infinity. Let's see. So which test you'll be using for this question here you want to see? Any suggestions? So the series is summation n goes from 1 to infinity, and it's n times e to the negative n squared. Anyone who knows? Ratio test. Ratio test work, but it will be a little bit. It will be a little bit hard actually. So yes, because you see that if you change n to x, this looks like x to the e to the negative x squared, right? That's something we can definitely evaluate very easily. Does that make sense? So if you look at, because fn is n equals to e to the negative x, and the integration of 1 to infinity x e to the negative x squared dx actually equals to, let me make a u substitution, u equals to x squared. So this is from 1 to infinity again. E to the negative u, I guess there's a du and there's a 1/2 here, right? Which we know is converging by just finding out the integration here. Okay, so this actually is finite by the integral test because this integration is finite. So this original series is also converging there. Okay. Has Dr. Chadwick actually talked about discussed about the integral test in class? Or he just sketched about these?
We did the integral comparison. Oh no, no. Yeah, we did the integral test.
Oh, you did it. Okay. Because I mean, remember, so this is what I'm trying to see. Suppose on the final exam, yeah, so I think that this should be the kind of questions using integral test is so limited. I mean, there's only up to three, no more than three kind of questions so far in this class that has been tested. Because it's so limited, I want you guys to see all of them to remember for which case you want to use integral test before the exam, so that you won't be, searching for other kind of techniques. So this is
If I
one.
remember correctly,
Yeah,
the only thing he went over was e to the n.
e to the n. So this is some kind of like derivative of that. Okay,
Yeah.
n times e to the n negative n squared. So the point is, whenever you see a form that looks like something that you can integrate, then go to integral test. But don't try this until every other method has failed. Okay, so don't try to use integral test. This is so integral test should be your last result to solve the problem. You should always consider the comparison principle at the beginning, at first. If it doesn't help you, if the alternating series doesn't help you, if every other method doesn't help you, then you go to the integral test. That's the point. So let me give you another example using integral test. For example, another example would be something like n squared e to the negative n cubed. So you see the similarities between these two examples here, right? And also it could be something like, I don't really have too much because I mean, because there aren't many examples involving these. Let me see if there's one good one on the textbook. I think there's one actually I remember in the textbook. Okay, let me see the corresponding chapter on integral test. Let me just get to there. Yeah, this one. This is one I want you guys to remember actually. This is actually one exam question. Okay, something like this. Can you guys read clear what I'm writing here? It's 1 over n times log n. Okay, if you want to determine if the series is converging or diverging, in this case, you won't be able to use any other method except integral test in this case. Okay. Do you guys know how to do this actually using integral test? Yeah, definitely try this one. I would say that try this one. Let me see. Another example would be something like this. N goes from 2 to infinity, n times log n squared 1. Okay. So really remember these two forms and also this one here. Okay. These are the only possible cases where you'll be using integral test on the exam, to my knowledge, actually. The reason why to do that is because you notice here, in this case, the n and the n squared give you an indication that you are doing some differentiation here, remember? So that means it's a u substitution. And the e to the negative u is something that we can integrate. So that's why we do the following thing. And in this case, you see that what's helping you here is if you do a u substitution taking log n to be u, then 1 over n is nothing but du. And here you have 1 over n here again to help you. So these two factors are a good hint that we are going to use integral test. Okay, remember these three examples here. Okay. So once we are done with integral test, then the next one is let's do some alternating series test. The alternating series test is the following example, which is actually very easy. It's -1 to the nth power, n cubed, n to the 4th power plus 1, taking summation from 1 to infinity. And also, sorry, let me go back a little bit to examples. You can see that I'm using n start from 2 because when n equals to 1, the denominator doesn't make any sense. So that's why I avoided n equals to 1 from the beginning. Okay. So, but in our case, this one, there's no problem with that. So n start from 1 to infinity, -1 to the nth power, n cubed over n to the 4th power plus 1. And in this case, it's very easy to see. This term goes to 0 when n goes to infinity because this is the degree 3 polynomial. This is the degree 4 polynomial, which grows faster than the denominator, than the numerator. So this thing goes to 0. And also it's decreasing because it's really hard to see it's decreasing, but you should be able to check that using calculus, the way I mentioned last time, by taking the differentiation of this expression with respect to n and find out for which n will f prime x smaller than 0. Okay. So this is another example where when n is maybe larger than 1, this will be start to decrease actually. So yeah. So this is, you check the decreasing property and this check the limiting goes to 0 property, and both are satisfied, hence it's converging. So next example is something like summation n goes from 1 to infinity, 2 to the kth power over 2 to the nth power over n. Let's see, n factorial. Okay, so this should be clear which test we want you guys want to use, right? Because you see that not only you have 2 to the nth power, also you have n factorial. Both are a strong indicator that you'll be using the ratio test. Okay. So in this case, you look at 2 to the n plus 1 over n plus 1 factorial over 2 to the n over n factorial. And the limit of that, when n goes to infinity, actually equals to, I think it's 0, right? So that means it's actually converging. Make sense? This is smaller than 1, right? Sorry. So this is converging because of the ratio test. Okay. So another example would be the following. Suppose you have summation n goes from 1 to infinity, 2 plus 3 to the nth power over 1. Okay. Which test you want to use in this case? Any suggestions?
Would it be the comparison test?
Comparison test, yes. And compared to which series?
1 over 3 to the n.
Which is it's a geometric series, right?
Yeah.
Yes, perfect. So we compare this one to 3 to the nth power. And you can see this is converging. So this should give you a very good sense that this should be converging then. And the right way to do this is smaller than that, because you are making the denominator smaller, so the whole series becomes larger, but this is also finite, and so this is finite too, and that infers the original series is converging there. So this inequality here is crucial. This inequality, this direction is what we want. Because if you get this direction here, if this is larger than something which is finite, doesn't tell you that this is finite, right? To see something that is finite, you better say it's smaller than something which is already finite. And that's the proper way to argue using logic, right? So this is correct. Okay, so that's actually the kind of like I'll give you some very easy examples to see, to have a good sense of the converging test. So let's look at some more examples before we move on to the next topic. So the next topic is about some more examples. The first one is, let's look at maybe tangent 1 over n. Let's see, summation n goes from 1 to infinity. Try this one. Can anyone find out if this one is converging or diverging? Okay. A good hint of this is we know that limit x goes to 0, sine x over x equals to 1, and the limit x goes to 0, cosine x equals to 1. That's the two hints I give you to you guys before you actually try on this problem. Okay. Okay. Any suggestions? So suppose that you know this two equality here. When limit 1x goes to 0, sine x over x equals to 1, the limit 1x goes to 0, cosine x equals to 1. What does this two limiting behavior tell you about tangent x? Can you see something about that? Anyone who want to share some ideas? So if I write something like this, let me see. Actually, it's something like this, right? This is tangent x over x, right? What's the limit when x goes to 0 for this expression here? When x goes to 0, this expression equals to sine over cosine over x, right? Which further equals to, sorry, I'm writing backwards actually, which further equals to this, right? This is, what I'm doing is nothing but because you notice that this is actually sine over x times cosine. I'm just grouping it in different ways, remember? But then when x goes to 0, sine x over x equals to 1, whereas cosine x goes to 1. So the whole limit actually goes to 1. Does it make sense, this argument? When x goes to 0, let's see, plus. Any questions about this, this line of argument? Okay, so I will assume that you guys all followed up to this step. But what does this equality mean? This equality means that when x is really small, tangent x behaves almost like x. Okay, but why is that helping us? Look at this expression, the original series. When n becomes very large, 1 over n is very small, right? Then tangent n is almost like what? It's almost like 1 over n. Does it make sense? So when n is large enough, tangent 1 over n is almost like 1 over n. Does this convince you guys that's the right way to think about tangent 1 over n? Okay. So if that's true, that means we can compare tangent 1 over n, this series, with a p series, which is 1 over n. And the latter one, the summation of 1 over n is the harmonic series, right? Which diverges, and it's a fact we know from previous lectures. So that means this one also diverges, okay? But to quantify that, we do a limiting comparison principle, right? Okay, so this is the right logic to do it. So based on this argument, you know that your original series is comparable to 1 over n. And then to rigorously argue that, you actually do this computation. And then based on the result, which is 1 not equals to 0, then you know that the original series actually diverges. As long as this is finite, then it's done, right? Because they will be converging or diverging at the same time, actually. Okay. Any questions about this example here? Okay, so let's try. I think that's probably enough, but let me give you an exercise for you guys to do, actually. Maybe no, this one is too hard, actually. Anyway, so let's, yeah. What else I have? Let me see if I forgot anything I want to say to you guys. I think that's, yeah, that's pretty much everything I want to mention about the testing part on theories. Okay, so now let's move on to the next one, which is power theories, and how do you think about this, and how do you find the interval convergence? Okay, so let's now move on to power series, and in particular the radius and the interval of convergence. Okay, so let's look at the following example. The first example I want to do is this one. Let's look at -3 to the nth power over x to the n over square root n plus 1. And the summation goes from 1 to infinity. Let's see. We are given a series like this, a power series, which is written as -3 to the nth power times x to the nth power square root over square root of n plus 1. We want to find out what's the interval convergence for this series. Okay. So to determine the interval convergence or radius convergence, so we let an go equals to -3n times x to the nth power over root n plus 1, right? We write down this as a series. So then an plus 1 over an with x value then equals to the x value of -3 n plus 1 x n plus 1 over root n plus 2 over -3 to the nth power times x to the nth power over root n plus 1 x value. Okay, which after simplification, if you group them into different terms, you get -3x in the numerator, and then you get root n plus 2 times root n plus 1 as a limit, as a result when you do the cancellations, everything. And this actually equals to 3x times root n plus 1 over root n plus 2, right? The negative sign can be dropped because it's actually x value there, right? So then what's the limit when this one goes to infinity? You see that they're actually comparable, right? When n goes to infinity, this term goes to 1 as a result. Make sense? Sorry, let me move it. So this one actually goes to 3x as n goes to infinity. Okay, this should be easy to see from this step to here, right? And then letting this to be smaller than 1 tells you that you want x to be smaller than 1/3. And that tells you the radius of convergence is exactly 1/3. So this is actually the radius of convergence. Okay. Does this make sense? I mean, this example should be a very standard template model case where we solve these kind of questions. Is we set up the AN, we look at the ratio, taking absolute value, and finding the limit when n goes to infinity, and letting the result to be smaller than 1 and solve for x, which will be inequality for x, and that gives you the radius. But once we have that, then the next thing is to determine the boundary behavior, because now we see that we have 4 possibilities for the interval convergence. We have this one, we have -3, this one, we have -3, 1/3, this one, or we have closed case. Okay, we don't know which one it is for the interval convergence. So let's test the series on the boundary points, meaning we are going to plug in values for x to see if the resulting series is converging or diverging at these 2 points. Okay, so let's see at x equals to 1/3, your series is nothing but n goes from 1 to infinity, -3 to the nth power, 1/3 to the nth power over root n plus 1, which equals to summation n goes from 1 to infinity, -1 to the nth power, 1 over root n plus 1. It's an alternating series, right? So on the right boundary point, your original series, power series, becomes an alternating series, which actually is decreasing to 0 for the nth term. So this one converges here. So that means the series actually is the interval should be closed on this side. So that means it's these 2 possibilities that we are looking at, right? And then we look at the boundary point x equals to -3. When you do something similar, you see that the negative side, actually, the sign part got canceled out because you have a -1 to the nth power again. And -1 to the nth power squared is 1 squared. So it's always constant sign. So this becomes summation 1 over root n plus 1. Okay. And from this side, we can see that this is almost comparable to 1 over root n, which is a p series. And this one diverges because p is 1/2. So that means this one diverges on the left end point. So by comparison principle, this one actually diverges. Okay, so it diverges on the left hand side. So that means our result should be this one. The interval convergence is actually this one, the open closed interval. That is the right answer for this question. Okay, so any questions about this example here? Everyone's good? Is everyone still here? Okay, so yep, that's the interval convergence. So any questions about what you have learned so far from the lectures? Has Dr. Chadwick mentioned anything about the final exam yet? So what's the format of the final exam, and what will be included and excluded for this exam, for this semester actually? Okay, I see. But it's definitely going to be an open book test, right? I mean, since no one's going to come back to school, I guess. Maybe they're actually developing some kind of software for you guys to take the exam online, I guess, like a web assignment or something like these, so that the exam can be taken uniformly for everyone. But let's wait for that. But he's sure that the complex numbers won't be on the final exam, right? What about the polar coordinate? Has he mentioned about the polar coordinates? No means it's not on the exam, or it's going to be on the exam actually. Okay, perfect. That's actually perfect, because polar coordinates can be annoying actually. It's not useful for you are not going to use it for next semester if you're going to take the calculus 3, I guess. it's going to be a very small example for CAX3. So yeah, okay, let's see. If you have a chance, do ask him if polar conics will be on the final exam or not. Make sure about this, because each year there's some question, there's at least 15 points worth of question on polar conics, which I don't want you guys to miss if every other section, I mean, if other instructors section know it and Dr. Chadwick didn't know it. I don't want you guys to suffer from that. So definitely make sure about this. Okay. So that's about interval convergence and everything like this. So before we do, before I leave you guys free, any other question from the worksheet? Do you guys know how to do the finding the power series expansion for given function using integration and differentiation rules? Do you guys trust yourself on doing something like that? Do you want me to do an example or maybe 2 examples on that, or you guys can do it on your own? Okay. So let's see a small example on power series expansion, because I think that this is actually very, it's not hard, it's just like you have to understand some basic things. So let me write down a list of functions going from easy to hard. Let's see that this is the very first one. This is the next one. And this is the third one. And this is maybe the fourth one. Okay. And then there's another one. Let me write down another one. Let's see. Has this been complete enough? Maybe another one would be this. Okay. So I consider this list as all coming from this basic model here, this 1/1 minus x. Do you guys know what's the power expansion for this function here? This should be the very beginning case that everyone should memorize or really know at the beginning of your solving this problem. So do you guys know what is 1/1 minus x as a power expansion? Yes, one, and the one will the first, where does n starts? N goes from 1 or 2 or 0. Yes, thank you. It's going from 0. Okay, so roughly speaking, this is 1 plus x squared plus everything. This is why geometric series is so important, because this is a, remember, this is a geometric series with initial term 1 and the ratio x, so it's 1/1 minus x. Remember these. This is our basic case. If you know that, then these 3 things will be something just about algebra. This is nothing about differentiation. So let's see that. What you get from here to here is by changing the sign of x minus x to x. So what you can do is this one becomes 1 summation n goes from 0 to infinity negative x to the nth power. So this becomes n goes from 0 to infinity negative 1 to the nth power x to the n. So it's an alternating series. You guys see that? And this is nothing but substituting everything x to be negative x squared. Remember, it's negative x squared. If I write like this, you should see the similarity between these 2 expressions. 1 minus x, 1 minus x squared. So if you think about this as a box, this is 1 plus box squared, right? So that's why we can do this kind of substitution, because it's very formal, right, in terms of the relation here. So this becomes n goes from 0 to infinity, negative 1 to the nth power, x to these 2n in this case. The 2n correspond to x to the second power to the nth power again. Okay. Then what about this one? This can be a little bit trickier, but it's actually very easy if you stare at this for a couple minutes. What you are looking for is nothing but a summation of many polynomial terms, right? And you already know how to do it for this one. So let me write it in this form. If I write it like this, in this form, my hint is the following. We know what's the power series for this one based on the strategy we have been using for the previous case, right? You just substitute everything for x in terms of to be -4 x squared, right? In this series, original model case. But how do you do with the x to the third power multiplication here? Like I mentioned, since the power series is nothing but a bunch of x to the nth power added together with different coefficients, this term serves as a shifting in the exponent. So let's be more explicit. So we know this actually equals to x cubed, n equals to from 0 to infinity, -4 to the nth power, x to the 2nth power. You guys agree with this expression? Right? This is nothing, excuse me. This is nothing but taking the power series expansion for this term alone, right? And then multiply it by x to the third power to everything here. Now the crucial step from here is that you can actually multiply this inside the summation sign and then adding the exponent 3 to the corresponding 2n here. So everything becomes actually summation n goes from 0 to infinity, -4 to the nth power, and x to the 2n plus 3's term. You guys see that? That's how you merge the x to the cube power in the numerator into the power series expansion. And this is a valid power series because this is nothing but a bunch of x to the nth power added together with different coefficients here, right? So it's a power series, okay? And that's how you do it whenever you see multiply by a given power series, by a polynomial term like these, okay? Once we know that, then let's look at the very last one. The last one is where you have to use the following relation is this actually equals to d over dx 1 over 1 minus x, right? If you look at this equality here, 1 over 1 minus x squared actually equals to these by the chain rule here, okay? So that means you can differentiate the corresponding polynomial, which is n goes from 0 to infinity, x to the nth power, okay? And then for differentiation, you can actually shift the differentiation inside the summation sign. That's called differentiation term by term, right? So this becomes summation n goes from 0 to infinity, d over dx to the x to the nth power, which equals to summation n goes from 0 to infinity, x to the n minus 1 times n, right? But you realize when n equals to 0, this is 0, so there's nothing there. So that means you're actually going to summation n goes from 1 to infinity, also n times x to the n minus 1. Okay, that makes sense? How you get this kind of shifting from here, from n equals to 0 to n equals to 1. Okay, so be careful with this subtle change in the initial term here. Okay.
Oh, could you just explain one more time why you took the derivative for that one?
Which line? You mean this
Yeah.
second one?
Yeah, just that whole line right there. Why did you take the derivative?
So first of all, do you recognize that 1 over 1 minus x squared actually equals to the differentiation of 1 over 1 minus x? This is nothing but differentiation here.
Okay.
Yeah, if you differentiate 1 over 1 minus x, you get 1 over 1 minus x squared, but the chain rule hits on 1 minus x, that's give you another minus 1 there, right?
Yeah.
So the two negative sign cancel and becomes positive. So that's why this actually is the differentiation of the 1 over 1 minus x.
Okay.
Actually, this is something I want to actually see is that whenever you see 1 minus x to certain powers, if you're asked to find the power series expansion, that's always related to differentiation rules. Okay. You always have to first find out what's the differentiation rule between these two things, this thing and the thing that you already know. Okay. Given these two equation, what I'm doing in the second step is nothing but taking the expansion of this term inside the bracket to be summation x to the nth power. I'm doing the power series expansion for these alone without doing any differentiation first. Then in the next step, by the differentiation, the theorem of differentiation for power series, I can move the differentiation inside the summation sign and differentiating the power series term by term. By that, I mean I can just differentiate x to the nth power and then add all the terms together. That's how I get to the fourth term, this equation here. But one very last thing you should be doing is you have to find out what's your very initial term, what's your very first non-vanishing term. It's actually correspond to n equals to 1, and it's not n equals to 0 anymore because n equals to 0 got canceled out. Okay, so that's how I get from here to here. So let me give you another example, actually, since you asked. I mean, another example related would be 1 plus x, actually. Let's look at this. Okay. In this case, you first find out log 1 over x is nothing but 1 over x dx, right? We know this. And this actually equals the integration of summation n equals to 0 to infinity negative x to the nth power dx. Do you guys all agree? Okay. So then what you're going to do in the next line is this actually equals to integration from n to 0 to infinity integration negative x to the nth power dx. Again, I'm using the integration and differentiation rules for power series. I can move the integration inside the summation to do it term by term. And this gives me like summation n goes from 0 to infinity. What's the integration of negative x to the nth power? It's like a negative 1 to the nth power x to the n plus 1 over n plus 1, right? This is nothing but how do you call that? The power rule, right? And you get a constant here. The kind of subtlety here for integration rule is not about the first index. It's actually about this constant, right? How do you determine the constant? Because they are using some kind of implicit differentiation here. So this actually equals to, so when n equals to 0, this becomes constant 1. So then you determine the c by the following. You notice that log 1 plus 0 actually equals to summation n equals to 0 to infinity negative 1 to the nth power 0 to the n plus 1 over n plus 1 plus c, right? You have this equality here, but log 1 is nothing but 0. And this side, when n equals to 0, this becomes, when n equals to 0, this becomes x, right? So everything here is nothing but 0. So that means your c should be equals to 0. Okay, so that means log of 1 over x actually equals to summation n goes from 0 to infinity negative 1 to the nth power x to the n plus 1 n plus 1. And that's how you find the power series for log 1 plus x. You see this, compare this case with the following, this one here. When you have 1 over 1 minus x squared, you are doing the differentiation to the original model case. When you have log 1 plus x, you are doing integration to your model case. And that's the whole content of differentiation and integration theorems for power series. Okay, so remember this very basic example here, and let's see some more complicated ones. So suppose you are asked to find out the power series for tangent inverse. You'll notice that when you differentiate this, what's the differentiation of tangent inverse x? Or maybe a different question is, what is tangent x, inverse x, in terms of integration there, maybe?
Like the integral of 1 over 1 plus x squared.
Exactly. Oh, sorry. Okay, so compare this one, log 1 plus x to tangent inverse x. For this one, do you know how to do that now if I have this equality here? Right? You do the basic case, you do the power series expansion for the inside. You have a power series, and then you integrate that term by term, and you sum that to be something like this, right? You get some expression like this plus c. And then when x equals 0, tangent inverse 0 is 0, and you compare that and find out the value of c, and then you solve the whole problem. Does it make sense? Just by having this equation here, gives you everything about gives you every information you need to find a power series for these, actually. And also another similar question would be to find power series maybe for, I guess, what's another one? Yeah, I think this is actually good enough, actually. Yeah. So let's talk about something about on the exam. So you may wonder, if this is the only way you can find all these power series? Is this the only way we can do that? Let me ask you guys the following question. Can we find the power series of these functions involving tangent inverse x? Can we do something different to find the power series for these? Anyone know that? But do you guys know how to compute the Taylor polynomial of these functions? Do you guys know how to do that?
Isn't finding the Taylor polynomial going to be the f of 0 plus f prime of 0 over 1 times x?
Yeah. So basically, you have that model, that template, right, to ask you to compute the Taylor polynomial of that. Actually, you can find the power series expansion for all these functions by computing the Taylor polynomials, maybe the first few terms, and see if you can find a pattern from there. But that's going to be a very hard way to do this. So the easier way to do this would be what I just showed, what I have just showed to you guys by doing the algebraic way to do this, all starting from this base model here. But if you have a question which is very general function f(x), and ask you to find the power series expansion, then the most efficient way to do that, in general speaking, is to actually compute the Taylor polynomial, maybe the first couple of terms, and see if you can find a pattern for the nth term, and determine the power series expansion from there. But later on, you guys will be learning the following functions. You'll be learning about sine function. You'll be learning cosine function. You'll be learning e to the x. And that's all the model case you should be memorized for the final exam. Or if you have a textbook, you should know where it is in the textbook. So sine x, cosine x, e to the x, and the 1 over 1 minus 4, 1 minus 1 over x. These are the 4 basic functions that we know how to compute the Taylor polynomial and the power series expansion explicitly. So knowing these 4 examples will be very crucial for this kind of questions. Okay. Any other questions about this kind of things? So everyone should be good. Okay, so perfect. And I think that's probably for today. Everything I want to mention to you guys. And hope you guys enjoy the lunch. And let's see you guys on next Tuesday. And if you have any questions, just email me. And we don't have a worksheet for today. The only thing that you want to do is try to, start reading the textbook, and also ask Dr. Chadwick if polar coordinates will be on the final exam, because I don't think we have enough time actually to go from today. Maybe we have actually, but I think we need at least 1 week to learn everything about polar coordinates. So yeah, definitely confirm with him if that's going to be on the final exam or not. Also, begin looking into the test bank and start preparing for the final now. Don't wait until the last minute. You should be starting as early as possible, because we only have almost like 2 weeks left for the semester to end. So I want you guys to actually start prepare for the final then. Okay, so I will see you guys on next Tuesday.
Awesome. Thank you, Bo.
Yep, thank you.
Take care.
Take care.